And we are ready. Thank you again. Um, as said from Professor Guarnaccia, I'm Domenico Rossi, a researcher in the Applied Physics Labs, and today I will speak to you about noise, introducing this work entitled Road Traffic Noise Prediction by Means of L10 Modeling with Multilinear Regression Calibrated on Simulated Data. We are switching on, we're covering another subject, and we are basically speaking about noise. Here we are. And a brief overall of this work. We started with the motivation why we want to measure noise. We created a model, so I will describe this model with the very particular data set that we built, we computed. Then the core of the work is the application of this multilinear regression technique, actually 2 times, and then a validation of this model and some conclusion and future steps. So we are dealing about noise. Why the noise is so important? Because as you can read here, um, through all Europe, a growing number of people are constantly exposed to a harmful level of noise. We're speaking nearly of more than 55 decibel 8 of noise. And as you can see from these infographics, it's in Italian because it's been made from an Italian agency, but it's been built with data of the European Environmental Agency sources. A constant exposure to a high level of noise can lead and bring to several problems to the health of people, starting from annoying all through the days, sleep disturbance, growing to more severe problems like healthy problems, and also sudden death. The main source of this noise is road traffic noise. We are constantly exposed to noise coming for traffic, so for cars passing by. So the assessment of the noise is very important for realize how this condition of our urban context, and also if we want to build some new facilities or some new roads or something like that, it's very important to know which will be the noise that this structure will bring. Noise measurement is made basically by measurement. So you can reach the site and measure the amount of noise, but sometimes it is not possible because for many reasons. So when it is not possible to have a measurement of noise, you can simulate the noise. If you have some reference measurements, then you calibrate a model and then you apply the model on a new site. But there's a problem. If you calibrate on one specific site and then you apply on the same site, the simulation has a certain amount, let's say, a specificity. But if you want to apply on a new source, this specificity goes down. So the idea was, why don't we compute a data set when we can calibrate a model, and let's check if this calibrated can be applied on different sites. So that's what we did. And we made the new traffic noise model. Basically with these steps, we generated a computed data set, and this bullet point here gives you the independent variables that we use it. So this stands from the source and the receiver, how many vehicles are passing for unit of time, the speed, the velocity of each vehicles, and how many heavy vehicles are passing. So then we computation this L10, that is an indicator for noise. We choose this L10, but actually we could have choose some other ones. Then we apply the multilinear regression coefficient, and then we validated on 2 real traffic data sets. This is the idea. Okay, this little scheme, you have a receiver, that is human being, at a certain distance from a road, and then you have an N vehicles. Each one has a different speed. You have heavy vehicles, that is measured with percentage of the whole car passing, and then you have the total amount Q, that is of cars, of vehicles passing for unit of time. Then we choose to compute the L10, which is the noise level, with this formula that we adapted from an original work that is cited here. And here you can have all the parameters. So again, vehicles per hour, each vehicle speed, the distance, the source between the source and receiver. This is very important. The power level that is computed with a peculiar noise emission model. But again, we choose this grammar, but we could have choose whichever model we wanted, and then the distance from the source and the receiver. This is not the linear distance, but you also have to take into account the height of the receiver. Once we computed the level out of the independent variables we computed in this model, as here, we performed a multilinear regression to see the dependencies between the L10 and all the independent variables, and then we get this coefficient of simple, very simple multilinear, simple, concept is simple, or the multilinear regression model, and also the intercept. Here you can see that we assessed the collinearity between all the variables. Then we performed a second step of multilinear regression, but that is this one, between the simulated values and the x. This x is made by each single independent variables multiplied by the coefficient we just found, the red numbers. And so we had this finally formulation. Of course, we calculated the residuals of the multilinear regression, and we had the new intercept value and the new slope values. With these red numbers we had here, and together with the ones we just calculated, we have the final formula, that is the second one, by which we finally simulated the noise level. And then, once we have a formula to simulate noise level, we want to assess the specificity and the validation of this model. So we choose two different sites. These are two cities, and when some noise data, raw traffic noise data has been collected in India and in France, and then we simulated the noise level using the same data sets, and then we calculated the error by using of these metrics, mean absolute error and root mean square error, very, very easy. Let's start with the first one. It is a city of Patiala in India. It's a straight road, 4 kilometers abroad for the city of Patiala in India. And the measurement has been in this, you can find in this work, and has been measured with a class 1 sound level meter at 8.5 meters away from the center of the inner lane. And here you can have a statistic of all the noise, of all the parameters, the same parameters, of course, we use it for the simulation. And in this violin plot, and of course also in the table, you have the distribution of the measured noise level, the blue ones, the simulated noise level. The yellow one is the noise level simulated with our model, with the presented model. And then we also made a comparison between two models, the models of the court models, which is, the European standard for the noise assessment, and this red one, which is the original work by which we took and modified, the formula for the L10 calculation. As you can see from the table, both the error metrics are below, are lower than the one obtained with the other models. So we have a 0.93 decibel A of mean absolute error and 1.16 of root square error, mean error. Then we move to the second one, to the second validation dataset, which is in the city of Saint-Berthevin in France. Which actually, these data are in a very big project of collecting for nearly 7 years of noise level collecting, not also noise, performed by the University Gustave Eiffel. And again, is this statistic of the data set. And again, the same structure, measured data in blue, our simulated data in yellow, simulated data with court in green, and the simulated data with this work, say our reference work. And again, we have error values lower than the other models. And in this last slide, you can see the two models, the two data sets together. This is the simulated levels of L10 versus the measured level of L10. We divided in blue and red the two data sets, the Indian one in blue and the red one in the France one in red. And these are the mean error values and mean root square error values that we already presented in the slides. As you can see, our levels are always lower than the other two. So to conclude, starting from the idea of a computed dataset that can apply to different sites to simulate noise, the assessment of noise level, we apply the multilinear regression to calculate an indicator. Again, I want to stress that we choose an indicator, but we could have chosen some other ones. There's also a formula to convert from one indicator to another. And we validated on two different data sets. And the mean error in each case is below 1.5 decibel 8. In the meanwhile, we also went in deep on this work with another paper that has been recently published, and we slightly modified the computing of the data set by applying, for example, a repetition on each random set of variables to improve the specificity of the model, and performed also some outlier analysis. And we choose the hyperparameters of the regression model to, to improve this work. And as you can see here, these data are still not published, but just to give an idea, this is the standard, the mean and the standard deviation of the errors when we validate on the two data sets. And as you can see from the first and second graph, as long as the data set is bigger, as long the standard deviation of the error goes down, so you can repeat many times as you want, and the error goes slightly down. And yeah, that was the last slide, and I would like to thank you for your attention.